Hello everyone, welcome to Understanding Physics, in which I'll try to guide you through understanding physics. So today on Foundational Mathematics, we're going to talk about the functions of complex variables, in which it is dealing with functions, but you are putting in complex variables in, and then you get complex variables out. So before we get started, please consider liking and subscribing, and also please check the notes in the description for the notes throughout this entire discussion. So before we get started, I'll be first display every single topic that will be discussed throughout this entire video. So first we'll be discussing about what is an analytic function, analytic functions. After that, we'll be talking about the analytic functions, but we'll be describing it using power series, defined by power series. And then we'll be doing calculus of analytic functions. And then after that, we'll be taking from the calculus of analytic functions and find that we have something which we call as the residue theorem. Residue theorem. And thus from this residue theorem, we will later be able to develop the Taylor series for analytic functions. Analytic functions. So if you want to skip through for these other topics, you could go ahead and look at the timestamps shown here. So let's first discuss about the analytic functions first, but before we go and dive straight into analytic functions, we should discuss what is a complex function. So this complex function will be a function which converts a complex number into another complex number. And so this function from a complex number to another complex number could be described as fx.y equaling to ux.y plus I vx.y. So what this entire notation really means is that you could express a complex number in terms of a coordinate system like x and y, and then the output will be a function of u as well as a function of v, which are both real functions. And what you get here is a complex function. So remember when we discussed about multivariable calculus, one thing that I didn't describe was continuity. And so how do you describe continuity for a multidimensional function? So this all comes back to the idea of the single variable continuity, in which it must have definite limit. Definite limit. So what does it mean to have a definite limit? So it means that if you go from any different side towards a certain point, it must to equal that. It must to equal, sorry, it must be the same. So if you go in the x direction, y direction, xy direction, all of them has to be the same limit. That's the first criteria. The other is that it has to be equal to the value at that point. What I mean is the limit. The limit must be the same as the actual value of the function. And so this is pretty much obvious when you talk about single variable calculus, and you could extend it towards multivariable calculus. So I'll just give a very simple example in which if you have x squared over x squared plus y squared, if you go in the x direction, if you go x towards 0 and y is constant, what you would get here is it's gonna be so the y is 0, that means it will be x squared over x squared, which is going towards 1. But if you take x equals to 0 and then y towards 0, what you would get here is 0. And you could do other different paths and it will give you different values. So this is what you call as a non-continuous function. Well, this is still a real function anyways. So this definition will be kept at the back of our minds because this will later describe what is a analytic function to begin with. So we could now start to discuss the idea of a analytic function. And the way that we do it is that we could express x and y in terms of z and z star. So you could convert between these two, and the reason is that z is x plus iy, and then z star is x minus iy. And so you could do algebraic manipulation to get x in terms of z and z star, and then y in terms of z and z star. And then if you put them in, it will become a function of z and z star. But if we actually try to consider where the function only depends on z, you get something which you call as an analytic function. But if it is only considering z star, that means that the function is anti-analytic. And so if you have an analytic function, f of z, you could take the derivative with respect to z because it's only one variable. So the df is like the df over dz times dz, right? But here's something interesting. We know that z is x plus iy. But we could also express this as dz equals to dx plus I dy, which means we get certain information from this. dz over dx at constant y, must equal to 1, and then the dz over dy at constant x has to equal to I. So these two informations could be substituted in. And the way that we do this is that we could express this as df over dz over dx at constant y times dx. It's the same thing. And this will result in this is the same as df. It will be df over dz times dx. And then at the bottom side, it's df over dz over dy at constant x times dy. And this would equal to, so if we substitute it in, we get I times df over dz times dy. And this gives you two different equations. The first is the df over dz is the same thing as the df over dx. The second, df over dx, df over dz is the same thing as, idf over dz is the same thing as df over dy. So because these two things are both a function of df over dz, we could just do a substitution. And so we would conclude that this would be df over dy is the same thing as I df over dx. And this is the criteria of a analytic function. You could try to develop this much more further by actually substituting it back with the f equals to uxy and I vxy. So it would be the u of y plus I vy is the same thing as I times ux plus I vx. And this would later conclude to the idea that ux must be vy and uy must equal to negative vx. And you could just do this pretty much by simple algebra and just figuring out that those two things has to be equal. So this type of property must to exist. So this is what we call as the Cauchy-Riemann equation, CRE. So anti-analytic functions also have this type of property as well. So now from the CRE, let's try to define what does it mean for a function to be analytic within a domain. And the simple way is to actually describe it like this. A function is analytic in the domain D if, first, from here, we see that the partial derivative must exist. So ux vy uy vx exist. That's the first criteria. The second is that they have to be continuous. They must exist. They also must be continuous, because if it is not continuous, it could have a jump, which would mean that one of the derivatives would be going towards infinity, and so this is not really allowed. And lastly, what it needs to obey is the CRE, as the CRE literally defines what does it mean for a function to be analytic or not. So you could do this with multiple different examples and figure out that it's analytic throughout the entire domain, or sometimes it is not really analytic at one certain point, and etc. But we could also define something which we call as the analytic. F is analytic at a point. Analytic at point z0, let's say. And the way that we do this is that we'll just use the same definitions, but instead we will use the domain to be the epsilon neighborhood. So what does it mean for something to have an epsilon neighborhood? This is where if you take a point and then you take a very small circle with radius epsilon, there exists a epsilon such that the point has to be analytic. Sorry, the domain has to be analytic. And this is what does it mean for a point to be analytic, is that it must be analytic for this very small domain. So we'll do some examples. So let's just state that if we have x squared minus y squared plus 2ixy, and we'll just check if this is analytic or not. We could just do the first derivative. At the front, it's 2x equals to the derivative at the back with respect to y. It's 2x, which is the same. And then negative 2y, same thing as negative of the back derivative with respect to x to y, which is the same. Which means that we figure out that it is pretty much, it exists for all x and y. But let's try the example of 1 over x plus iy. And we'll just do the derivative. Well, we should actually just re-express this in terms of x squared plus y squared and x minus iy. And let's try to do the Cauchy-Riemann equation. So first, we could just take the derivative. At the front, it's x squared plus y squared minus x times 2x over x squared plus y squared, everything squared, must equal to the derivative at the back, which is negative x squared plus y squared minus the function, so it's positive 2y squared over x squared plus y squared squared. So this is for the first equation. For the second equation, it's going to be negative 2y over x squared plus y squared squared plus to equal to the negative of, at the back, it's going to be the negative at the front, it's going to cancel it, and it will have negative again, so it's still negative, and the back with respect to x, it's going to be 2x over x squared plus y squared, everything squared. Sorry, my bad. There should be a multiple of x as well, and multiple of y. And these two are also the same. But this is not really an analytic function at the point x equals to y equals to 0. And the reason is that it is not really defined at this particular value of 0, 0. It goes to infinity. And so this is a reason why 1 over z is not really an analytic function at every single domain, but it is still analytic throughout the other domains. And so this is the idea where we'll develop the idea of singularities. So singularities are points in which it is not really analytic, and there are multiple of these. So first we have something which we call as the simple pole. A simple pole is pretty much the one that is exhibited from 1 over z. And so we'll actually develop some ideas if you have function z over z, and then if you take limits very close to it, sorry, rz, if you take values pretty close to the origin, you couldn't really define what a function is. But if you take the limit as the z goes to your z0, so this z minus z0, sorry. So if you take the limit of rz over z minus z0, but you multiply this by z minus z0, you would get the residue. Or this could be called as your function anyways. So this is what we call as the residue. So the residue is a term for you to describe how high is a simple pole. It's pretty similar to talking about how high a pole is. The next one is the nth order pole. So the nth order pole could be described by 1 over z minus z0 squared. So this one could be described by doing the same thing by taking the limit. But instead of doing z minus z0, you multiply your function z by z minus z0 to the power of n. So a property between a simple pole and the nth order pole is that a nth order pole actually increases much more drastically compared to a simple pole. It's like going much more faster. But there are also some other poles which actually goes to a indefinite value pretty fast, which is something which you call as the essential singularity. Essential singularity. So this is where, for example, you could take the sum of 1 over n factorial z minus z0 to the power of n. And so you couldn't take any value of n because it's going much more faster. It's going from 0 to infinity. So any type of function that, sorry, any type of z minus z0 to the power of n doesn't constrain your function here, which is why it is called as a essential singularity, because it goes much more faster. Lastly, we have the branch point. So the branch point is where, let's just take an example. Square root of z is a type of branch point. And we have shown this in the previous video, in which if you take square root of r e to the power of I theta over 2 plus pi I, this corresponds to a positive 1 and a negative 1, which means that it's going back and forth between the two values. And so this gives a conclusion that if you take a certain complex number, it could have two different values. It depends on your phase. So this is the idea of a branch point, exactly, in which a particular point has two different values thanks to this type of singularity. So throughout this entire discussion, we'll be talking about the meromorphic function. So a meromorphic function is a function in which everything is a pole. It's the singularities as all poles. So previously we are able to derive the relation for a analytic function in terms of the derivative. df over dz is the same thing as the df over dx, which is the same thing as I df over dy. Sorry, the I should be at the bottom. Now, we can also gain another property just by doing the Cauchy-Riemann, and then you take the derivative. So let's say ux equals to vy, uy equals to negative vx. And let's show you this property for one of the function, and then you could do the same thing for the other function. So you could take the derivative with respect to x for the top one. It's going to be uxx. Will be the same thing as vxy. Now, here's the thing. Vxy and vyx is the same as long as v is continuous. And so because v is continuous, we could just state that this would be the same thing as Vy of x or Vx of y. Now Vx of y is already defined to be Uy with respect to y again. And this is Uxx. And this gives the relation Uxx plus Uyy is 0. And this is what we call as the Laplace equation. Or you could also call this, and you could call the solution as a harmonic function. So this is very evident when you're dealing with oscillation, is that the double derivative is the same thing as the negative of the double derivative. It already corresponds to a wave equation. And so this is what we call as a harmonic function. So every single type of equation that follows this type of Laplace equation is called as a harmonic function. Now we can try to jump into the idea of the power series for an analytic function. And the way that we do this is by actually defining the series first. S must be equal to the sum from 0 to infinity, right? From 0 to infinity of your function an. And then you could do tests for you to figure out if it is convergent or not. And it is only convergent if its real part and the imaginary part are convergent. So there are tests such as the ratio tests, or you could test if it is absolutely convergent to figure out that your function is also convergent. So there's pretty much lots of tests that you could do. Now for the power series, s equals to from 0 to infinity of an z to the power of n, z minus z0, sorry, because it's centered at z0 in general. You could figure out that this is convergent if you do the ratio test. So the ratio test will give you an plus 1 z minus z0 to the power of n over an z minus z0. Sorry, this is technically absolutely convergent, okay? So we just take the absolute value of this. And so this is pretty much the same thing as the absolute value of an plus 1 over absolute value of an, absolute value of z minus z0 to the power of n, and z minus z0 to the power of n. Oh, sorry, this is n plus 1. This is n. So now with this, we could derive that an plus 1 over an must be the z minus z0 here. And so we could develop that this has to be less than 1, right? So z minus z0 has to be less than the an over an plus 1. Or this is what we call as the radius of convergent previously. So this is already pretty evident when we talked about the infinite series, is that we have the radius of convergent to be only two different parts that goes from negative and positive. But in here, we see why it is called as a radius. It is like a circle. So this is what we call as the radius of convergence, in which every single point of this entire circle tells you that the function is convergent. So with this idea, we could actually develop functions, but not only simple functions. We could do multiple different series of functions that we have already developed from the real function. So some functions include the e to the power of a z, and this is already defined to be the sum of n factorial of z minus z to the power of n from 0 to infinity. And this also works for imaginary numbers. Now this means that we could actually do this for sine, cosine, cosh, and sinh. And in fact, they have a relation between each other. So you know sine z to be in terms of eiz minus e to the power negative iz, and then cosh is e to the power z plus e to the power negative z over 2, and etc. And if you rewrite it in terms of those, and then try to figure out the relation of multiplying it by a complex number, let's just take cosine of iz, let's say, you could actually figure this out to be e to the power of iz minus e to the power, I and then I negative iz plus over 2. And this is the same thing as e to the power negative z plus e to the power z over 2. And this is the cosh of z. So this is the first relation. The other, sine iz, is the same thing as, we could do the same thing, e to the power negative z minus e to the power z over 2i. And this will be the same thing as I sinh of x, of z. So we also described the Taylor the series of the natural log of 1 plus z. And we found this to be the sum of over n and negative 1 to the power n plus 1, z to the power n, where z must be less than 1. So we could actually convert this into the natural log of z. So to talk about the natural log of z, what we would do is that we could actually try to express, let's say, z equals to r e to the power I theta plus 2 pi n. Now, this has to be written as natural log of r plus I theta plus 2 pi n. This is inevitable because we're expressing this in terms of an exponential. But notice this. What we got here is that we still get the natural log of r, which is something that we expect if we put a real number. But we don't expect that there is multiple different values of the natural log. And this is a very interesting property of the natural log, is that if you put one function, it will give you a spectra of solutions in the imaginary plane. And this also concludes why, let's say, z to the power 1 over n, for n equals to a natural number, to have multiple different values, or n different values to be precise. And this is because if you take this and take the e to the power, you would get r times e to the power I theta times e to the power 2 pi n over n. Now the value only repeats if n equals to the big N. So there is this repetition of n times. It's like splitting your circle, let's say 5 times, would mean that it is a power of 5. Well, this is 1, 2, 3, 4, 5, 6, 7, 8. This is like 1 over 8. This is the solution. And it gives you a clue why if you take the power of a rational number, it gives you a very specific solutions. But if it is a power of a irrational number, there's an infinite solution there's an infinite solution. So now let's talk the calculus of analytic functions. So we'll just only start from a very simple idea. So from calculus, well, you could just do term by term. You could just do term by term integration or differentiation, and you would still get your solution straight away. But it will be pretty complicated for you to do that. So instead, what you could do is that you could just, let's say if you have a function, and then you take a very particular path. And let's try to figure out a relation of this. So the circle here corresponds to an integral over the entire region. It's gonna be the fz dz, right? But you could substitute your values in, right? So this is like the circle integral of x point y minus v x point y. No, you know what? Let's don't write it like this. So we'll just express fz in terms of uxy minus I plus I v xy, and dz is gonna be corresponding to dx plus I dy. Now to make it much more simpler, what we'll just do is that we'll just do a very particular type of contour. It's just a rectangle with a very small distance called dx again. And we'll try to do the And so by doing this type of contour integral, it will be much more simpler. And also we get a very elegant feature. So you could just do this on your own. So if you want more discussion of it, you could just you could just ask it in the comments for me to describe it in a much more further notation. But anyways, what we could do is that we could re-express the integral into the following. It's the negative uy minus I vy minus vx plus I ux dx dy. And so you could get this by first figuring out that uxy has an integral. Assume that to be big U of x, and then you do it for others, and then you do it for every single path. And what you would get is that you could actually pair them up to get its first derivative for the big U of x, and then after that you combine others so that you could get a double derivative in terms of a big U of x, big V of x. But then because you know that the big U of x is just the integral of dx, it will later cancel each other out, and you would get the following equation. Now this following equation only works if your function is continuous, which is the definition of a analytic function. But not only that, it has a definite u and v partial derivatives, it's continuous, but if we assume that it also obeys CRE, Vx equals to negative Vy, and Ux equals to Vy, what we would gain is that this would equal to 0. Now this gives you a very elegant clue, is that if you even take any type of path, you could combine these small contours, and later the paths will later cancel each other out and form this big contour. Now this big contour here must also equal to 0. So the idea is pretty simple, is that if you stretch your contour across the domain, it would still have the same type of integral. And with this idea, you could slice it off into different paths. And these different paths will later still obey that the one that's going in this direction must be the same as the one going in this direction. Otherwise, the contour integral has to be 0. This subtle clue actually gives you a very elegant piece that taking the integral from z1 to z2 of fz dz is just the integral of your analytic function. It doesn't matter how you go towards the other point. As long as you go to the other point and then you do the integral, it will still have the same solution. You could also do this by pretty much just doing the integral. So let's just do an example. Let's say z squared from z1 to z2 of dz. You could just simply do it by taking z cubed over 3, substituting z1 and z2 straight away. That also works. So it is just a function which only depends on its states. So from this, we could actually develop the idea of the residue theorem. So because we figure out that the circular integral has to be the same, but let's just do something which is not really analytic, 1 over z. And we'll just do the contour integral, where it contains the non-analytic function. So if we do this contour integral, because it's not really analytic throughout the entire domain, it could not follow it could be that it does not follow the contour integral must be conservative. So if we do this, you know what, let's just do this. And instead of doing this straight away, we could just substitute z equals to r e to power I theta. So what we'd get dz is r e to power I e to power I theta d theta. So substituting that in, well, technically this is dz over z equals to I d theta. So we substitute this in. So from 0 to 2 pi, which is just a circular integral of I d theta, it's going to conclude that this is 2 pi I. And in fact, if you do this for a residue, you would get the following information. The contour integral of function z, if it has residues, it will be just 2 pi I with the sum of the residues. It's pretty much just that. And you could have multiple different residues to obtain a much more higher form of 2 pi i's. So this is evident if we actually only assume that it is an analytic function, it doesn't have any singularities, it shouldn't have any residues, which means it would equal to 0, which means that the contour integral equals to 0. Now this type of fact is actually very useful because the way that we could actually express this much more further is that if, let's say this is z0, okay? So it has a residue at z0. So, wait, technically at n equals to z0 or whatsoever. It's just the sum of the residues. But if we try to re-express this, so this is non-analytic. Non-analytic non-analytic on the whole domain. But what we could do is that we could just re-express this because we're just assuming this to have only simple poles. We could just re-express this as fz minus z0 dz. And we do the same thing. It's 2 pi I rz0. But this time we'll just assume this guy to be analytic. So now with this, we could actually just take the first derivative straight away with respect to z0. This is like the Cauchy's... No, sorry. It's the Feynman's technique. You would get the circular integral of fz over z minus z0 to the power of n, the squared dz, plus equal to 2 pi I. Oh, sorry, the residue is actually a function z0, which means this is df over dz0. Now this gives you a clue. Because we know that fz over z minus z0 squared is definite for values other than z0, it means that df over dz0 must exist. But this could be extended much more further. We could go further and further to obtain that n factorial over 2 pi I with the circular integral of fz over z minus z0 to the power of n plus 1 is the same thing as, must be the same as dnf over dz0 to the power of n. So with this fact, we found that it always exists. The derivative of the nth order must exist for a analytic function. And now we could extend this further into the Taylor series, because we know every single derivative exists. We could just use the Taylor series. Fz equals to the sum of d over dz of f to the power of n when n goes from 0 to infinity times z minus z0 to the power of n. This always works for analytic functions. So there's a proof of this, but I will fully discuss like how do you derive it, because doing the derivation is pretty long, but anyways, this is already pretty intuitional. If you already know about Taylor series, is that you could just re-express everything in terms of these guys, and then you take the derivative and it turns out to be the same. That's a simple idea of doing the Taylor series. But the derivation pretty much tells you that the Taylor series is not really designed just by matchmaking, but instead it comes from all these residue theorems. So something interesting about the Taylor series is that even though so there is always a radius of convergence, which we have here. So Taylor series only works if it is within the radius of convergence. But something that is very useful when we're doing this Taylor series is that even though if it has a radius of convergence, but something that is also a very cool property is that the Taylor series actually doesn't have any singularities. You pretty much disregard your singularities. So throughout your entire domain of convergence, it doesn't have any singularities. But it is also unique, based on the property of the power series. If you have a different Taylor series, it means that it has a different function. The next one is that every analytic region has a Taylor series. So first it disregards singularities, but other regions will also have its Taylor series. And here's something interesting, is that if you actually take Taylor series, let's say from here, and it has a radius of convergence, you could take another Taylor series from here and then do another computation and gain another radius of convergence. And so this pretty much encapsulates the entire domain except for the poles. So this is a very cool phenomena where you could just disregard your singularities and just look at your Taylor series. As long as it's convergent, you know that it is not a singularity. Finally, it has the property of the permanence of functional relations. This means that if a property holds for a certain domain, as long as the property is something that is still viable in terms of the analyticity, the property propagates throughout the entire domain. So let's say something like the relation of sine x plus sine squared x plus cosine squared x equals to 1 first only works at the real value, but because of the permanence of functional relations, in which you figure out that e to the power of x is actually e to the power z, and e to the power e to the power iz and e to the power negative iz, it tells you that it could actually propagate throughout the entire domain, so that it actually works for even complex numbers. And so that's pretty much all of the discussion that we'll be doing for complex functions. And in here I did fully derive lots of the equations that you could gain, but you could use this information for you to derive the Taylor series, the residue theorem, and etc. But anyways, in here we'll be focusing on how do you apply these absurd ideas of the complex functions for your physics or engineering life up ahead. So thank you very much for watching, and make sure to like and subscribe, and also please share this to your friends who really needs to understand the mathematics behind physics in a much more deeper understanding. So thank you very much, and I will see you on the next video.